Imagine a universe less than a second old. It's a place of incredible energy, where temperatures are unimaginable. This is the Hadron Era, a crucial phase in the universe's infancy. It lasted from a mere microsecond to 1 full second after the Big Bang. It's a period defined by the emergence of structure from the primordial soup. The Hadron Era followed the quark epoch, a time of fundamental particles. Before this era, the universe was too hot and dense even for quarks to exist. As the universe expanded and cooled, the Hadron Era began. This marked a significant shift towards the universe we know today. This era is not just a chapter in the early universe's story, it's a cornerstone. It's the period where the seeds of matter as we know it were sown. The echoes of this era resonate even today, billions of years later. Understanding the Hadron Era allows us to peer back to the very beginning. It lets us unravel the mysteries of the universe's formation and evolution. The Hadron Era is named after a class of particles called hadrons. These particles are the building blocks of atomic nuclei. They are composite particles made up of quarks. Quarks are even smaller, fundamental particles. There are two main types of hadrons, baryons and mesons. Baryons, like protons and neutrons, are made of 3 quarks. Mesons, on the other hand, consist of a quark and an antiquark. During the Hadron Era, the universe was teeming with these particles. The high energies allowed for the constant creation and annihilation of hadrons. This created a dynamic and chaotic environment. The formation of hadrons was a pivotal step in the evolution of the universe. They provided the raw material for the creation of atoms. Without hadrons, the universe would be a vastly different place. The Hadron Era was a time of extreme conditions. Temperatures reached trillions of degrees Celsius, hotter than the core of any star we know. These high temperatures were a remnant of the Big Bang's energy. At such high energies, particles moved at incredible speeds, close to the speed of light. They constantly collided with each other, creating and destroying particles in a chaotic dance. This extreme environment had a profound impact on the behavior of matter. The laws of physics, as we know them, were different. It was a universe governed by the principles of quantum mechanics and relativity. The high temperatures and energies of the Hadron Era played a crucial role in shaping the early universe. They dictated the types of particles that could exist and the interactions between them. Before the Hadron Era, quarks and gluons existed in a free state. They formed a hot, dense soup called quark-gluon plasma. This exotic state of matter is thought to exist today in the cores of neutron stars and in high-energy particle collisions. In the quark-gluon plasma, quarks and gluons moved freely, unbound by the strong force that confines them within hadrons. This state is characterized by its high energy density and its ability to flow like a fluid. As the universe cooled during the Hadron Era, the strong force began to dominate. Quarks and gluons combined to form hadrons. This marked a significant change in the properties of the universe. The study of quark-gluon plasma provides valuable insights into the fundamental nature of matter. It helps us understand the behavior of particles under extreme conditions. Section 5. The birth of protons and neutrons. One of the most significant events of the Hadron Era was the formation of protons and neutrons. These particles are the building blocks of atomic nuclei. Their creation paved the way for the formation of atoms. Protons and neutrons formed through a process called hadronization. In this process, quarks combined to form hadrons. The specific combination of quarks determined the type of hadron formed. Protons, consisting of 2 up quarks and 1 down quark, and neutrons made of 1 up quark and 2 down quarks, emerged as the dominant baryons. Their stability and abundance would later shape the universe as we know it. The formation of protons and neutrons was a crucial step in the evolution of the universe. It marked the transition from a universe dominated by quarks and gluons to one populated by the building blocks of ordinary matter. Section 6. A transformative shift from plasma to particles. As the universe continued to cool and expand, a critical transition occurred. The quark-gluon plasma, once dominant, began to disappear. This marked the end of an era. The decreasing temperatures meant that quarks and gluons no longer possessed the energy to remain free. The strong force, now dominant, bound them together into hadrons. This phase transition from a quark-gluon plasma to a hadron gas is a fascinating area of study in cosmology. It provides insights into the behavior of matter under extreme conditions and the fundamental forces that govern the universe. The transition from plasma to particles had profound implications for the future of the universe. It set the stage for the formation of atomic nuclei, and, eventually, the atoms that make up everything we see around us. Section 7. The matter-antimatter imbalance, a cosmic puzzle. During the Hadron Era, a crucial asymmetry emerged, the matter-antimatter asymmetry. This refers to the observed imbalance between matter and antimatter in the universe. In the early universe, matter and antimatter were created in equal amounts. However, a slight imbalance allowed for a tiny fraction of matter to survive the subsequent annihilation. This surplus of matter would eventually form the stars, galaxies, and planets we observe today. The exact mechanism behind this asymmetry, known as baryogenesis, remains one of the biggest mysteries in cosmology. Understanding this imbalance is crucial for explaining the existence of matter and the universe as we know it. Scientists are actively studying various theories to explain baryogenesis. These theories often involve physics beyond the standard model, suggesting new particles and interactions. Section 8. From simplicity to complexity, the first atomic nuclei. The Hadron Era witnessed the formation of the first atomic nuclei. These nuclei, the central cores of atoms, formed through nuclear reactions between protons and neutrons. The high temperatures and densities of the Hadron Era provided the necessary conditions for these reactions to occur. Protons and neutrons, brought close enough to overcome their electrostatic repulsion, fused together, releasing energy and forming heavier nuclei. The first nuclei to form were primarily those of light elements such as deuterium, a hydrogen isotope with one proton and one neutron, and helium. These elements, formed in the first few minutes after the Big Bang, are still the most abundant elements in the universe today. The formation of atomic nuclei marked a crucial step in the evolution of the universe. It laid the foundation for the creation of atoms and the subsequent formation of stars and galaxies. Section 9. Setting the stage for a new era, the transition to leptons. As the universe continued to expand and cool, the Hadron Era gradually gave way to the Lepton Era. This new era, commencing around 1 second after the Big Bang, marked a shift in the dominant type of particles. Leptons, a class of elementary particles that includes electrons, muons, and neutrinos, became the most abundant particles in the universe. The lower temperatures of the Lepton Era allowed for the existence of these lighter particles. The transition from the Hadron Era to the Lepton Era was a gradual process. As the temperature dropped below a critical threshold, the production of hadrons became less favorable. Leptons, lighter and less energetic, began to dominate. This transition set the stage for further evolution. In the Lepton Era, electrons and positrons, or anti-electrons, would eventually annihilate, leaving behind a small excess of electrons that would later combine with nuclei to form atoms. Section 10. The Hadron Era, a foundation for our universe. The Hadron Era, though brief, played a pivotal role in shaping the universe we inhabit today. It was a time of immense energy, extreme temperatures, and profound transformations. During this era, the universe transitioned from a primordial soup of quarks and gluons to a universe populated by hadrons, the building blocks of matter. Protons and neutrons formed, setting the stage for the creation of atomic nuclei and eventually, atoms. The matter-antimatter asymmetry emerged during this era, a crucial imbalance that allowed for the existence of matter and ultimately, our own existence. The first atomic nuclei formed, laying the foundation for the creation of stars and galaxies. The Hadron Era serves as a reminder of the incredible journey our universe has taken. It highlights the interconnectedness of the cosmos, where events in the first fraction of a second continue to influence the universe we observe billions of years later. As we delve deeper into the mysteries of the Hadron Era, we gain a greater understanding of our own origins and the fundamental laws that govern the universe.